All right. Cool. Let's talk about acids and bases terminology-wise before we jump into the practical so you guys know what you're looking at and why. So, are you doing that again? Don't do that. I think I need to get a new document camera. But they're very expensive, so I'm trying to avoid it. It's lasted me a long time, though. It's lasted me at least 5 years, I think. All right. So, now I got to find my markers. I thought I just had them. Oh, they're there. Okay. So, let's give some definitions of what acids and bases are. Is it still flicking? Stop doing that. Why are you flicking? Stop it. All right. So, when we classify a substance as being acidic, we are talking about something that is a proton donor. So, say, for example, it releases the H plus ions. Are we good so far with that? Just hopefully ring a bell. Acids have properties such as when you taste them, they're sour. That's the best way to kind of describe what an acid is. If I'm thinking about a pH scale, do you guys know what the pH scale is? Yeah, so the pH scale is referring to how acidic or basic something is. So on the pH scale, it would be a low number. Basically anything below 7. So when I'm looking at an acid, it's going to have a high concentration of the hydrogen ions, and it won't have a lot of hydroxide ions. Are we okay with that so far? Happy campers? All right, shall I talk about what a base is? Okay. Bases are basically the flip side of the acid. They are proton acceptors. The other thing that we can use to define acids and bases, and I should say that definition here is known as the Bronsted-Lowry definition. Bases can fall into different categories, but they all kind of do the same thing. So I'm just going to write that down in case you guys were curious. The other way that we can describe bases is that they release OH ions. That's going to drive me nuts. I might have to try that again. And that's the Arrhenius definition of it. So just be mindful. There's 2 different ways you can define it, but they all basically do the same thing. Did I spell that right? There's no S here. There we go. So that's what we're looking at for our bases. I'm going to just try to unplug that and replug it in, see if that gets it to stop flicking. Bless you. All right. Cool. And these guys have a pH that's a high number. We okay with that so far? It's hopefully ringing a bell. Yeah. All right. The other word I want to just throw at you guys, just in case you haven't seen it before, is amphoric, which means that it has both an acid and base component. Can you guys think of one that's like that? You guys have learned a molecule that is amphoric. Water, yeah, because it can be both a proton donor and acceptor. There's another one. You learned about inorganic. Starts with an A.
Ammonia.
Amino acids are your example of that. So basically, they can act both as a proton acceptor and proton donor. Are we good with that so far? All right, let me just write out reactions for you guys to see. So the other thing that we need to think about when we're thinking about acids and bases is also neutralization and things like that. So I just want to I'm just trying to think of an example of one that I like. So we know that we have an acid such as hydrochloric acid. And let's say we put a base with that, such as sodium hydroxide. So we mix those two things together. Those things are going to neutralize. And our byproduct will be a water and a salt. So in this case, if I was looking at this reaction here, that would be H2O, and that would be NaCl. So that's what we're looking at when we're thinking about neutralization reactions. I'm stuck. All right. Let's try to find what I'm looking for. Acids and bases. Oh, now I remember what I wanted to do. All right, so there's other words that I need to teach you guys about acids and bases, and that's known as conjugate acid and conjugate base. So some of the things we got to think about is when these guys dissociate in water, say this guy over here, we have HCl plus H2O, dissociates in water, and what we form is H3O plus and Cl minus. Are you guys okay with that so far? All right, so this here is my acid, and we see that it is given a hydrogen ion to the water, so that makes it the proton donor. And then the water here is my proton acceptor. So in this case, this is acting as your base. Are we good so far? Right, we have to be mindful that when we're labeling things in the product side, that we're thinking about what happens if it goes in reverse. So if we're thinking about this going in reverse, you see how this has the extra hydrogen ion. So if I was to go backwards, this here is your proton donor, and then that's your proton acceptor. So we call this your conjugate acid. Since that's going to now be the donor of the proton. We use the word conjugate when we're talking about those products. And this is going to be known as my conjugate base. So I just want to point out those words so that way when I talk about them later, you know what I'm referring to. Are we okay with that, or do you want me to give you another example? Another example? I can do one with the base. So like, for example, if I have CO3 2 minus, so this is my carbonate, and I have some hydrogen ions floating around in my acid. Actually, we'll have H2O. So in this case, we see how we have H2O and we have carbonate. One of those hydrogen ions can go onto that carbonate, forming bicarbonate. And the OH minus. So if I was looking at my vocabulary here, this is my base because we see how that's the proton acceptor. The water in this case is acting as an acid because it's donating its hydrogen ion. So that's why I'm saying that there's molecules that are known as the amphiphoric molecules, and those are the ones that can be, amphiphoric molecules, which can be at both acidic and basic properties. So that's how water is able to do both. So that's going to be my proton donor, and then this is my bicarbonate, and that's my hydroxide. If this reaction was going in reverse, this guy would be donating the hydrogen ion back to the hydroxide, so that makes the bicarbonate the conjugate acid. And that's the conjugate base. So what you're basically looking for when you're trying to label things is who's donating the proton, who's accepting it. And I like to point those words out because we're going to have to use them later when we're looking at the neutralization reactions. Are you okay with that so far? Right, next bit. Okay, so the other thing we need to think about is that pH scale. So when we're thinking about pH, remember that we are referring to the negative log of the hydrogen concentration. So basically, if I know the concentration of the hydrogen ions that are in my solution, I can figure out the pH of my substance. We can also go in the other direction as well and use the pH to figure out the concentration of the hydrogen ions. So if I want to do it in reverse and I want to figure out how much do I have hydrogen ion concentration wise, what I can do is 10 to the power of the negative pH value, and that tells me how much I have hydrogen ion wise. So that's the relationship between those two. What you have to remember is that pH is based off of the logarithmic scale and not just a normal scale. So when we're comparing and contrasting those numbers, yes, it may only be going up by a small amount, but in fact, it is a tenfold jump from one to the next one because it's logarithmic. Are you okay with that so far? So one of the other things to keep in mind is how the pH of our oceans have changed over time. So before the Industrial Revolution, does anyone know what our pH was? Our pH was roughly 8.2. So our oceans are a bit acidic. So oceans pH pre-industrial revolution was 8.2. Now the pH is currently at 8.1. So that is a 0.1 pH change. Now it doesn't sound like a lot, but because we are talking about a logarithmic scale, it is a bigger number than what it looks like. So roughly, when I was doing the research, it's about a 30% decrease over that time. And what we're going to learn about is why that has happened. What is kind of concerning for us is that over the next century, if we continue with the trends that we are experiencing at the moment, we should expect the pH to drop to possibly 7.8 to 7.1 is where we're thinking that the new pH is going to land in about a century's time. So that's a change of 0.3 to 0.4. Again, it doesn't seem like a whole lot, but it is a logarithmic scale, so that is quite dramatic. And in fact, if our trends continue as they are, and our pH does drop to 7.8 or 7.7, that's going to be the lowest the ocean has been in 20 million years. And so we're going to learn about the impacts of it dropping. So that's why we're referring to ocean acidification, is because the oceans themselves are actually becoming more and more acidic. So that number is dropping. And we're going to learn why is that a problem. All right, any questions so far? All right, shall we do a practical? Take a little break. All right, so what I have done is I've gotten out some acids. Oh, actually, let me grab the PowerPoint so you guys can see it. I'll just pause the notes.